All right. So chapter 11 is kind of a big chapter. It's a wide encompassing chapter all about solutions. We're going to focus today. We're actually going to go out of sequence. We're going to go out of order here. And the reason we're going to go out of order has primarily to do with the fact that we want to touch on some things that you saw in lab this week that are going to inform some of the stuff that you're going to be doing in the next 2 weeks in lab. So we'll come back and talk about the stuff in the first 3 sections. We'll do that as part of Wednesday's lecture. But today our focus is going to be on concentration values. And so when we talk about concentration measurements, there are some calculations that are involved, and there are some terms that are involved as well. So we're actually going to start chapter 11 here in the middle, section 4, measuring the concentration of solutions. Now, what you should have seen in lab this week is that concentration is a measurement. Tells us the relative amounts of one part of the solution and the other. And when it comes to describing these things qualitatively, we use words like saturated. So a saturated solution is one where we've got as much solute, that is the thing that is being mixed in, we've got as much in there as can possibly go in there. It is saturated. No more will dissolve at this point. That's what saturated refers to. So if I make a saturated solution and then I try to add more to dissolve, that more will not dissolve. We can refer to a solution as unsaturated if it does not meet that criteria. So anything that has less solute in it then the saturated amount would be considered an unsaturated solution. So kind of an easy way of thinking about this. Let's say that you make some iced tea at home. Now, when you brew the tea leaves and you make the iced tea, initially speaking, there is no sugar in that tea. From the standpoint of it being a sugar or a sweet tea solution, it is unsaturated. There's nothing in it. As you add sugar to it, it is going to remain unsaturated until you hit the point that you can no longer add sugar to it and the sugar actually dissolves. Once we hit that point, then it is a saturated solution. We've added as much sugar as it can possibly take. All the extra sugar that we add just sits there on the bottom and collects. We can describe the solubility of a substance based upon what that concentration is at that time. And we usually measure it in grams per 100. So if I have 100 grams of tea, how many grams of sugar fit into that tea? That would be my saturation limit. That would be my solubility. Now, of course, there are a number of ways that we can manipulate our ideas of solubility. For example, again, using the iced tea example, if you add the sugar while the tea is still warm, is going to hold more sugar than if the tea was cold. It's going to dissolve faster as well. Well, the thing is, as that happens, ordinarily, if you make a sugar solution in warm water and then let it cool down, what eventually happens is that the sugar will start to crystallize inside. Kind of think about what happens to honey. If you've ever had honey crystallize on you, you put it in the microwave, it warms up, it redissolves. As soon as it comes back down in temperature, it recrystallizes again. That's what normally happens. But there are some circumstances where that doesn't happen, where I can heat up a solution, get it to dissolve more solute than what we should expect, and then gradually cool it down. And instead of crystallizing out like we would expect it to, it stays in solution. Now, this particular kind of circumstance is a rather rare one, but the solution that is created from it is something called supersaturated. It has more dissolved in it than the saturation limit. And they actually have some pretty cool properties associated with them. But one thing that we do know about them for sure, these particular solutions are kind of unstable. They will stay dissolved so long as they are relatively undisturbed. Start to move them around, shake them around, introduce little particles of dust or something like a seed crystal here. And what happens is that it'll crash out all of the extra solid. And we'll see these big crystals start to form as a result. Good example of this is with sodium acetate. I'll show you a video of that right here.
The flask contains a supersaturated solution of sodium acetate in water. A small crystal of sodium acetate will be added to the solution. Focus your attention on the portion of the solution to which the crystal is added. Here is the process again in slow motion.
Now, the camera work's not the best on this one. They don't actually show the crystal hidden.
Here is the process again in slow motion.
But you can see this right here is where that seed crystal landed. And you can see almost immediately what's happening here is that as that seed crystal finds its way into the solution, it starts to grab some of those other ions and help build and grow the crystal from there. And that's why it kind of snows out here, kind of like what we think of when you see, pictures of an avalanche or a really, really heavy snowfall. As those crystals start to branch out and touch other ions, the crystal starts to grow and grow and grow and grow and grow until we get to the point where it completely takes out most of what was there. So that's what happens in supersaturated solutions. We see this growing, we see this solution that is stable so long as it is undisturbed. We call that condition metastability. So it's metastable. looks stable, acts stable, but you give it just a little bit of a bump, a little bit of a push, and it shows just how unstable it actually truly is. So that's supersaturation. So again, those are all qualitative terms. These are terms that describe things without numbers, other than a solubility limit for saturation. Our primary focus today are going to be on quantitative representations of calculations of concentration. Some of these you have seen already in lab. Others of these are direct derivatives of something that you saw in lab that we just need to explain a little bit further. When it comes to concentration, there are really 4 different kinds of units to look at. There's the percent by mass, which you saw in lecture, or excuse me, you saw in lab this week. There's a percent by volume, which is calculated the same way, only using volumes instead of masses. There's mass volume percent, which is kind of a blend of the two. And then there's molarity, which you saw again in lab this week. With our remaining time today, we're going to go through each of those 4, what their definitions are, and we're going to do some calculations with them as well. So let's start with percent by mass. Percent by mass is one that you, even before lab this week, we were familiar with percent by mass. We talked about percent by mass when we talked about empirical formulas and mole calculations, going back probably about 2 months now. Percent by mass can be measured as the mass of solute divided by the total mass of solution multiplied by 100%. We did something similar to this again in that percent composition unit when we had mass of element A divided by total mass times 100%. It's the same calculation. The only difference is our terminology. Instead of looking at any element in a chemical formula or any element in a mineral or any element in a mixture of materials, we're talking specifically about the solute. We're talking specifically about the thing that is dissolved usually in water. And then the total mass of the solution is everything put together. If we are not given the total mass of the solution, we can always find that mass by adding together the mass of the solute and the mass of the solvent. So if I am told I have 30 grams of sodium chloride and 300 grams of water, they together would make 330 grams of solution. And then all I would need to do to find the percent mass is plug in the correct values in the correct places. 30 divided by 330 times 100% would give me 9.1% sodium chloride. So these kinds of calculations are generally speaking pretty simple. We can measure the masses directly using a balance. And then it's a matter of adding and subtracting to get the correct values and putting them in the equation in the correct way. One of the more common mistakes is forgetting to multiply by that 100 there at the end. A lot of people will get to this and go, okay, it's 0.091. It must be 0.091%. Got to remember to multiply that by 100 to get to that 9.1%. So that's percent by mass. Let's do another example. What is the percent by mass concentration for acetic acid in a vinegar solution that contains 2.7 grams of acetic acid and 122.8 grams of water? Well, very similar to the example that I just did. To find the total mass, I need to add those two numbers together, 2.70 plus 122.8. That would give me 125.5 grams total. To find the percent by mass, I need to take the mass of the acetic acid, 2.70 grams, divide by the mass of the vinegar solution in total, 125.5 grams, multiplied by 100%, 2.70 divided by 125.5 times 100% to three significant figures would be 2.15%. So the percent by mass here is 2.15%. Any questions with this example? All right, go ahead and try this one yourselves. What is the mass percent of sodium chloride in a solution prepared by adding 10 grams of sodium chloride to 50 grams of water? All right, we all seem to be on relatively the right track there. So first thing that we had to do, had to add together the two masses to get the total mass, then take the ratio to three significant figures. This would be 16.7%. So that's percent by mass. And again, you saw percent by mass in lab this week. That was what you had to do with the iron 3 chloride, the first iron 3 chloride solution. Percent by volume is pretty much the same. And if you look, the formula looks almost exactly the same. The only real difference is this. Total volume cannot be added. Total volume must be measured. And the reason we have to measure total volume is because volumes are not additive in solution. So it's possible that you can have 50 milliliters of water and 50 milliliters of another liquid, like alcohol or something like that, and only end up with 80 milliliters of total solution. the alcohol and the water kind of fit in each other's spaces and take up less volume collectively than they did individually. You have to measure total volume. Other than that, the calculation is essentially the same. Volume of solute, that is the thing being dissolved, divide by total volume times 100%. And because that part is the same, the calculations are all going to look very, very similar as well. So take this example. To make a solution, we dissolve 205 milliliters of ethanol in enough water to make 235 milliliters. What is the percent by volume concentration of ethanol? Well, in this case, that's our top value. So percent ethanol is going to be 205 milliliters divided by the total volume of 235 milliliters multiplied by 100%. $205 divided by 235 multiplied by 100 to three significant figures would be 87.2% ethanol. Now, fun fact, ethanol and water solutions are often sold over the counter, but they're not sold by percent by volume. They're sold by proofing. So if you ever look at the proofing labels for different types of spirits, the proof number is basically just double the percent number. So in this case, this would likely be sold as 175 proof alcohol. Wouldn't be my first choice, but that's how, if this existed, that's how it would be marketed. Proof labels are just percent alcohol doubled. All right. The third type of calculation is something called mass volume percent. Now, mass volume percent is a little bit different. Where we see this most often are solids dissolved in water, usually. So probably one of the most common applications is in the medical field. You know, nursing, ER, EMT. If you've ever encountered a saline bag, that saline bag is 0.9%. Now, that is not a volume because sodium chloride doesn't have a volume to speak of. It's not a liquid. And it's not a mass volume or a mass either, although it probably could be. Those kinds of things are usually weight by volume or mass by volume. The way that they're calculated is taking the grams of the solute, which is usually a solid of some kind, some sort of ionic compound or something like glucose or fructose or sucrose or something along those lines, and dividing it by the volume of the solution and then multiplying it by 100%. So if we think about that saline bag is 0.9%. What that means is that for every 100 milliliters of that solution, there are 0.9 grams of sodium chloride. Percentage just means parts of 100. So if I'm given a liter bag, that liter bag would have 1,000 milliliters in it. It would have 9 grams of sodium chloride in it. Again, pretty close to the same. The calculation is almost identical. It's kind of a blending together of those first two equations. We've got the numerator from the mass by mass, the denominator of the volume by volume. We're kind of smashing them together. We see this, again, most often for aqueous solutions with ionic or with solid components dissolved in them. The last calculation is something called molarity. Now, in a laboratory setting, and you've seen this, molarity is the most common way to express concentration. Because usually in a laboratory, we are concerned in some way with the number of moles of something that are present. And the molarity gives us an avenue by which to get to that number of moles. In molarity, we are calculating the moles of solute, that is the thing that is dissolved, divided by liters of solution. Of the four, this is the most difficult to get into because we have no way of directly measuring moles. I can't put something on a balance and have it tell me that I just put 3 moles of that something on the balance. It'll give me a mass, but I'm going to have to convert that mass into moles, doing a conversion using the molar masses from the periodic table first. And so that one extra calculation step is usually enough of a stumbling block that we do tend to make more mistakes with molarity than we do with anything else. Because everything else we've done so far has been really one-step calculations. You know, maybe I have to add these two numbers together first, but once I do, I put them straight into the formula, and it's easy and it's ready to go. With molarity, I've got to do an additional calculation step before I put it into the ratio. Notice one other thing. Notice the absence of that term right there. There's no multiplying this one by 100. And so one of the confusing parts out of your lab manual actually is the fact that in your lab manual, it does show that you multiply it by 100. That's not actually the case. That's not true. Molarity is just what it is. There is no multiplication factor in it. So let's do a couple of examples here. I have a solution that contains 117 grams of potassium hydroxide, KOH, in enough water to give a total volume of 2.00 liters. The molar mass of potassium hydroxide is 56.11 grams per mole. What is the molarity of the solution? So I've got 117 grams of KOH. What I need is I need moles of KOH divided by liters of solution. That's going to get me to my molarity. So I've got to somehow turn this into moles. And that's where those calculations that we did back in the moles chapter come in handy. I got to turn those into moles. Now, the way to do that is with the molar mass. So my conversion here, 117 grams of KOH. I need to turn the grams of KOH in the numerator into KOH in my denominator so that they cancel out. And I'm left with moles of KOH. My conversion factor Tells me that for every 1 mole of KOH, there are 56.11 grams of KOH. And so if I do my division, 117 divided by 56.11 to 3 significant figures, I will get 2.09 moles of KOH. To find the molarity, I need moles of KOH, 2.09 moles of potassium hydroxide divided by the 2.00 liters of solution to 3 significant figures, 1.05 molar, capital M, KOH. So what that says is that there are 1.05 moles of potassium hydroxide in every liter of that solution. That is the definition. That is what molarity means. All right. Any questions with this example? Okay, let's look at the other thing that you had to do in lab this week. Had to do with dilutions. Dilutions are useful because what they do is they allow us to decrease the concentration of a solution without having to make new solutions, without having to measure out new amounts of solid or of solute. And they do this by just simply adding more solvent. Now, you did this in the lab as well. You took that 5% iron chloride solution and you diluted it down to get it to 0.5%. What's interesting to note about dilutions is because we are only adding solvent, it doesn't change the amount of solute that's actually present. So take a look at these 3 pictures. I've got 3 test tubes with this green liquid in it. The green liquid are these green food coloring particles inside of each of the water samples. The only difference between number 1, number 2, and number 3 here is in the separation of those particles from each other. In number 1, those particles are closest together. The solution is the darkest in that particular test tube. In number 2, we've added some water that has separated some of the particles from each other. It has gotten lighter in color as a result. In number 3, we added even more water, and it separated those color particles even further from each other. It got lighter as a result. In each of those samples, though, we still have 5 of those particles. The difference between them is how close together they are packed. And the same is true for any solution that goes through a dilution process. We aren't changing the number of particles that are in the solution. What we are doing is changing the spacing between them. As we get more and more dilute, we get more and more space between the particles of solute. Now, when it comes to dilution, there are some terms that are necessary. First of all, a stock solution is the solution from which the diluted solution is made. So I've got a higher concentration solution. That's my stock solution. I'm going to use that to make the lower concentration solution, the diluted solution. This is different from what is called a standard solution. Standard solutions are solutions where we know their concentrations rather precisely. The two are not necessarily hand in hand. It is possible that we have a standard solution that is relatively dilute and would make a very poor stock solution. It is also quite possible that we have a very concentrated solution that we don't have a real good sense at what its concentration is. The two terms are not interchangeable. Although sometimes they can both be present. It is possible to have a standard solution that is also concentrated from which you'll make other solutions. The process of dilution is that process of lowering the concentration of the stock solution by adding more solvent. It works on the premise that the number of particles of solute in my stock solution is going to be equal to the number of particles of solute in my dilute solution. And so the form of the equation that we can use to calculate these changes is this. Now, you might see this equation rewritten in a number of different ways. C1V1 is equal to C2V2 is a common one. If we're talking about molar concentrations, M1V1 equals M2V2 is another common form as well. The reason we stick to the ones with the C's, however, has more to do with the fact of that this equation is more universal. So long as C1 and C2 have the same concentration unit, they can be any concentration unit. So I can use this equation, C1, C2, and it can be molarity, it can be percent by mass, it can be mass volume percent, it can be any of them. What's also important is that my V1 and my V2, those volumes, they can be any unit as well, so long as they are the same unit. So if I'm measuring small amounts, milliliters, microliters, nanoliters, or if I'm measuring large amounts, liters, gallons, whatever the case may be, so long as the two are the same, they can be used by this equation. And we'll stop here because this actually gets to something that we'll do in lab, not next week, but the week after. So on Wednesday, we will rewind the tape and go back to the beginning of this chapter to talk about those first three parts of the chapter. And then we'll come back and talk about titrations at the end of next week as we get into the acid-base unit. Have a great weekend.